Hello and welcome to Physics 1401. I'm going to wrap up this chapter with projectile motion, and you already know what the constant acceleration kinematics is about. We're just going to do it in 2 dimensions. That's what projectile motion is all about. Okay? So let's recall that in 1 dimension we have the following equations when acceleration is a constant. Well, we have 2 equations for displacement: v initial times time plus 1/2 a t squared. We also have delta x in terms of the average velocity times t, and the final velocity in terms of initial velocity and acceleration and time. And the 4th equation is without time, but in terms of initial and final velocities, plus 2a delta x. Okay, now this is along the x direction. I didn't use the index x like the book did, but if you want, you can add that x. Okay, x just symbolizes the x coordinate, of course. So these are the 4 equations. If you want, you can even write the 5th equation. You could express the 1st equation not in terms of v initial but v final, because these are related. All right. Now, what is projectile motion, and what does it have to do with this? Okay. A projectile is any object flying under the influence of gravity. All right. We usually ignore resistance, air resistance, which is a form of friction. So the only force acting on the object is gravity. Okay, so it's sort of a free fall, really. I mean, free fall means the same thing. Free fall is when you move under the influence of gravity only. A plane, for instance, is not a projectile because there's propulsion. Okay, the engines provide a second force in addition to gravity. But bullets, missiles, cannonballs, any ball, you throw a stone, or water, these are all projectiles, because once the ball leaves your hand, you're not pushing it anymore, you're not accelerating it anymore. The acceleration phase is when you're still holding the ball. Okay, when you swing it, you are accelerating it. But once it leaves your hand, it's just gravity. So free fall is also under that list. So a free fall in 2 dimensions, if you will. Okay, so you throw an object, you kick a football, you give it an initial velocity. What's going to happen to it? Okay, now I said gravity is the only force acting on it, so the acceleration is always downward. Now the direction of the velocity vector may and will change once you kick it, but the direction of the acceleration vector will never change. Okay, so at a later time, when the ball is about to hit the ground, v may point this way, possible, but a is still downward. Okay? A will determine how v changes. That's a different story. But its direction has only to do with the force, because F equals ma never changes. That's the governing equation here. And if Earth pulls an object downward, meaning its weight, this means acceleration is downward. Okay? And we saw this when we did free fall. Okay, you throw an object upward, it stops and comes back. Initially V was up, and then V is down. Doesn't matter, A is always down. Same thing here, just two-dimensional. So you kick a ball. Okay, so let's clean this up here. All right. Now what will be the path? Will the path be along the straight line? No, it won't be. It will not be, because the presence of A here, as time passes, will have an effect on V. V has to change, okay? So this V has to change. V as a vector can change by, can change in terms of magnitude. It also can change in terms of direction. A vector is magnitude and direction, okay? And that's what happens here. V will change in direction and also in magnitude. So let's take this equation then, since I mentioned it. But write it in vector form. What do I mean by that? Well, use arrows on top, but do not use the X. VI plus, now I have two objects here, T and A. T is a scalar. T is not a vector. T is time, right? It's just a number that you multiply your vector with. A is the vector. Right? AT or TA, doesn't matter. The order doesn't matter. That's your vector equation. Now, why did I write it like that? Because I have two directions now. X is horizontal and Y is the vertical. And as you know, every vector equation can be decomposed into its X and Y components. So we have two equations here that arise from one equation. One along the X direction, or V final X, let's say. V final, the X component of V final is equal to the X component of V initial plus X component of A times T. And also the Y, V final Y is equal to V initial Y plus AY T. That's the general case. I mean, this happens to everything as long as A is constant, okay? But since we're talking about projectile motion, where A is always downward, there is no AY. AY is 0, and AX is 0, sorry, I put it the wrong way. There is no X component. AX is 0. What about AY? That has the 9.8, right? It's 9.8 downward, but it's downward, so negative 9.8, or negative G. Let's go with negative G, where G is a letter that represents 9.8 meters per second square. Okay, so what happened here? We started with the one-dimensional kinematics equation, one of the four equations, and I said, write it in a generic form where we replace the variables with their vectors, which is like this, which lets me write that in two equations. Okay, if you consider the z direction, I mean, we didn't live in a three-dimensional space, you could even write this for the z direction. We don't need it, but you could. Now, why don't we need it? Because nothing is really happening in the z direction. Whenever you kick a football, once it starts flying, unless there's a wind, which will not be a projectile, simple projectile motion anymore, it will never bother to move sideways, okay? This velocity vector has a component, a horizontal component, and a vertical component. Now you may say, wait a minute, okay? I can go to a corner in my room and throw a ball diagonally to the other side, you may say. Okay, so if you want to challenge what I just said, you could do this experiment where this is your, excuse me, this is your room. Oops, sorry, that drawing. You're standing here, okay, you say, oh, this is my x direction, this is my y, and this is z, the third direction, okay? And you say, I'm throwing a ball, it's gonna go like this. So this velocity vector here will have not only x and y, but also z component. Then I would say, why do you pick your x, y, and y like that? You could rotate your xy, meaning you could pick this direction along the diagonal as your x, and z would be something that goes through the wall then, okay? So you can get to the third direction, that's what I'm trying to say. So we have two equations, and they can be really simplified because ax is 0, ay is negative g. So we end up with Vfx equals Vix, which is the most important thing in projectile motion. The x component of the velocity does not change all right, but we end up with these two equations. The x component doesn't change, and the y component does change according to this equation. So, going back to the question of what will be the path, it won't be a straight line, it will be what we call a parabolic path, like this. And along this path, when the ball moves, its velocity vector will always be tangent to the path. We've seen that before, why it happens. So tangent means this line here, for instance, and here's the velocity vector. At a later time, right before it hits the floor, again, you draw a tangent, and the velocity vector points in that tangent. So direction changes, but it's going to change in a way, in such a way that its x component is constant. See? So if initial and final correspond to these 2 points, let's say, the x component, which I'm going to show with green here, the x component, this is the x component, never changes. These two are equal, same length. What changes then is the y component, according to this relation here. The y component v initial y changes. See, it's now shorter here. This here is less than that. Less than v initial y. Why less? Because as time progresses, you're subtracting gt from viy. Vfy will be less than viy. And there will be a time when v final y is 0. When you are at the top. At the top, the maximum height Over here, you still have your horizontal Vx, that didn't change, but there is no more Vy anymore. Okay, that's when Viy is equal to gt. But time keeps running, so you subtract gt from Viy again, and then V final y will be negative. Say when you're here. See, it's pointing down now. Vy will be negative. Vx still same, whatever you started with. Okay? So this is the most important result, or the most important concept regarding projectile motion. The x component of the velocity does not change, but the y component changes. It goes from positive to negative if it follows a path like this. Sometimes the motion will stop before it reaches the maximum. You know, you're shooting an apple with an arrow, let's say. Okay, I mean, projectile motion can be applied in many different ways. So here's a tree, here's an apple, and you're going to shoot the apple with an arrow. So you aim it. But you got to keep in mind that this will be a projectile. So you don't aim directly at the apple, you aim above, so that by the time it reaches the apple, you want to hit it, right, like this. But what happens? The direction of the velocity vector changes. It has to change, okay? No matter how short the flight is, since there is gravity, the direction has to change. The initial angle here, say this was 45 degrees. Now this direction here is maybe 30 degrees. It depends on how far it is, of course. It will change, okay? So the y component changes, but the x component never changes in projectile motion. So let's write that component in terms of the initial angle then. V initial x is equal to V initial cosine theta. So this angle here is theta, and Viy will be Vi initial, sometimes called V0 by the way, V0. V0 is the same as Vi. Sine theta times Vi gives you the y component of the initial velocity. All right, so let's go back to our four equations. Now, we could do this for the fourth equation. What would we get if we did it for the fourth equation? Now, since the x direction, the x component doesn't change, we can see it from here too. Ax is 0, v final x squared is equal to Vix squared, which means the initial velocity does not change. But what about the y direction? We can write it. V final y squared is equal to V initial y squared. I'm going to replace ay with negative g, negative 2g delta y. Of course, x replaced with y. So I could use this equation here. Now, two equations here, one equation there, 3. Now let's go back to these for the first two. Now in the x direction, acceleration is 0. I'm only left with the first term. So delta x is equal to Vix times t. My fourth equation. Now look at the second equation here. Delta x equal to average velocity times t. Now Vix plus Vfx, if these two are the same, that's 2 Vix divided by 2 Vix. So I get the same equation again. Okay, so the first two equations give me one equation for delta x. And that will be the only equation with delta x in it, by the way. Now what about delta y? Delta y. Replace ax by ay, which is negative g, and vix with viy. Viyt minus 1/2 g t squared. This will be the fifth equation. And finally, take this second one and write it for y. Delta y equals viy plus what? V final y divided by 2 times t. This will be equation number 6. Numbers are not important. You can number them any way you like. But you end up with 6 equations for projectile motion. Okay? So those 4 equations of constant A kinematics are now, in terms of the coordinates, 6 equations. Okay? And the method for solving problems is pretty much the same. When you did the free fall, you looked at what's given and what you want to find. You're going to apply the same logic here. Just keep in mind, the x component doesn't change, but the y component of the velocity changes. All right? At the top, at the maximum height, the y component is 0, for instance. So let's go back to the football example again. Let me clear this a little bit. Let's start fresh. Oops. All right, so you give the ball an initial velocity of, I'm going to call it v0 now, just for a change, okay? v0. So you get familiar with different notations. And this angle here, I'm going to call it theta 0. Okay, 0 or O for origin. So the ball is going to fly in air and land here. Okay, my goal is to find that distance, d, the range. Okay. Find d in terms of v0 and theta 0. That's what it is. Now, when I kick a football, do I know what the velocity is? Well, you can't measure it. Okay. I mean, you may measure the angle, with some devices, but measuring the speed is not hard. It's not easy, but you can measure the range. Okay, so if I know the range in terms of v0 and theta 0, in practical problems, I could do it the other way around. I could take that formula and plug in the d I find from an experiment, and then find v0, for instance. Okay, that's how you can do it. So this problem of finding the range. How am I going to do that? Now, d corresponds to a displacement along the x direction. And among the 6 formulas I have, there's only one that has delta x in it, which is delta x equals v0 x t. Okay, going back to those 6 formulas. So I have to use this formula. There is no other place where I can find d. This is d, okay? d is delta x. The displacement is v0 x. But t is not given. T is not known. So we can't just do it without knowing time. Now I'm going to replace v0 x by v0 cosine theta 0, like we did previously, times t. But t is not known. Okay, so how do we continue then? T is not known, but there's something else we know, okay? Something else we know here. We don't know the final velocity. We don't know time. We know the displacement in the y direction. Delta y is known. Okay? Now y is up. Delta y is actually the difference between the final y and initial y. Both are 0. If I pick origin here, both are 0 and the difference is 0. Even if I don't take the origin right there, okay, suppose you're throwing the ball, you're kicking the ball, but you pick the origin somewhere else here, then you have a negative initial y, but the same y is your final y, so the difference is still going to be 0. Okay, so delta y is 0, and we're going to use that to solve for t in the delta y formula and plug that t in the first formula for d. So here's what we're going to do. Delta y is equal to v naught y t minus 1/2 gt squared, right? But delta y is 0. And v naught y is v naught sine theta naught. So this times t minus 1/2 g t squared is equal to 0. Okay, I could factor one of the t's because both terms have t, and divide both sides by a t. I would get 0 equals v naught sine theta naught minus 1/2 g t, not t squared, t, because I divided by t, right? Then I could solve for t, multiply everything by 2 and divide by g. So 2 v naught sine theta naught divided by g. Okay, that's my t. Take that t and plug it in here. So d will be equal to v naught cosine theta naught times t, which is 2v naught sine theta naught over g. And you can simplify it. You have v naught, which makes v naught squared. And you have cosine theta times sine theta times 2. You can remember this formula now. Sine of 2 theta naught is equal to 2, or any angle, 2 sine theta naught cosine theta naught. Okay, that's what we have here. So here then is equal to sine 2 theta naught divided by g. Okay, so that is the range formula that you have in the book. But it also tells you that the maximum range. So we have a formula for d given any angle. Now when you kick a football, let's say you kick with maximum force, which determines v naught. So you keep v naught the same, but what you can change is the angle you kick the ball with. Okay, so d becomes a function of angle only if v is kept constant. Which angle or what angle makes a maximum range? Which angle gives you a maximum range? What is the maximum? All right. Now to find that, remember that the function sine can take any values between -1 and +1. In one period, if you remember from trigonometry, some angle here, theta, and sine theta. These values that sine theta will have will be between +1 and -1, including 0, right? But its maximum is 1. So whenever sine 2 theta is 1, or whatever, or which angle makes theta 0, I'm sorry, the angle that makes sine 2 theta equal to 1 makes D a maximum, all right? Okay, so that is 45 degrees. This is 45. Okay, sorry, I meant when you're 90 degrees, sine theta is 1. If this is 90, theta 0 means 45. Okay, so if you kick the ball with 45 degrees, that's going to give you maximum range. .45 degrees. This will give you maximum range. 45 degrees. What if you kick the ball with an angle greater than 45? Let's say 70 degrees. It will be less. The range will be less. Okay, now it may go higher, and I haven't derived the formula for maximum displacement in the y direction, which I will in a minute. But it's going to fall short. Okay, this is maximum D. This is something less than that. So this is for 70 degrees. Now it turns out that there is one more angle here which will give you the same range. Now, do you know what angle that is? To find that, you can go back to this expression here, where you have sine theta times cosine theta. Okay, instead of using sine 2 theta, you can consider the product sine times cosine. All right, and from trigonometry, remember that we have complementary angles. Like you take 30 degrees, for instance. The angle that completes 30 to 90 is 60. Okay, sine 30 will be equal to cosine 60, which you can actually see from the triangle. Maybe it works better for you. A right triangle. Okay, so here you have one angle, I said 30, right? And here you have 60. A, B, C. Now when I say sine 30, I'm talking about A over B. Side opposite over hypotenuse. But that's the cosine of 60, right? Adjacent over hypotenuse. So you can apply this, and of course cosine 30 is sine 60. You can apply this to any angle, and it's complementary angle, which means that, for instance, sine 70 times cosine 70 is equal to sine 70 times cosine 70 is equal to cosine 30 times sine 30, right? So here's that angle, 30, which will give you the same range. 45 is its own complementary angle. Okay, whatever that word is, that's the angle that completes it to 90 degrees. Okay, so same thing happens with 40 and 50. They will give you the same, right? So here, let me use green. So this was 40, 50 would be something like this. And sorry, 50 would be here, and 40 would give you also the same, same range. All right, so one more thing, how to find the maximum height. How to find the maximum height given initial velocity and initial angle. All right. Now we got to remember that when you reach the top, your velocity is perfectly horizontal. All right. Which means the y component is 0. And we can use that. We can use that. So v final y, or vy, is equal to v initial y minus gt, right? Now there's a problem here though. This equation will not give me what I need, because this t is not the same as the t I found earlier. The t I found earlier was the total time. I'm talking about the t here. Instead, let me use the fourth equation, or whatever number that you like to give it. Vy squared is equal to v naught y squared minus 2g delta y, which becomes h. Okay, h. And vy is 0. Vy is 0, therefore 2gh is equal to v naught y squared. H is v naught y squared over 2g. But what is h max? Okay, now inside v naught y there is that angle. So if you write this explicitly, this is v naught squared times sine squared theta naught over 2g. Okay, but you know that 45 degrees gives you the maximum range. Okay, same principle can be applied here. So how do we get maximum height? Okay, now you have only theta naught here, not 2 theta naught. So when you're shooting directly upward, that's when theta is 90 degrees and sine 90 is 1. So h max is when you kick it directly upward. Theta naught is 90 degrees. Okay, so 45 for maximum range, and 90 for maximum height. You could ask what would be the height when you have the maximum range. Then you would just plug in 45 there. Okay, now there is another problem of finding the maximum distance when you're kicking the object from a height. Now this is a little bit more complicated, but not too difficult, and I actually solved it in another video, and I will include that link in the description for this video. The problem is, again, you kick the ball with an initial velocity, it flies like this, but now it reaches the it hits the floor over here. How do you maximize this distance? Range, right? What is the maximum range in terms of V naught and theta naught? Obviously, that cannot be equal to this thing we found here, this range formula, because delta y is not 0 anymore. You have the height, initial height, so delta y is negative h, okay? So, but you can find it, and I will give you the description. In the description, I'll give you the link to another video of mine where I do this problem. All right. So that's the theory behind projectile motion. Let's solve some problems, and I'm going to end after that. It's getting a little bit dark, so let me turn on some lights. Okay, better. Okay, let's find a problem from the book, a projectile motion problem. Okay, motion of projectiles. Let's start from the first one, number 38. A baseball is thrown horizontally from a height of 9.6 meters above the ground. .6 meters above the ground horizontally with a speed of 30 meters per second. VIX, right, in the X direction. All right, where is the ball after 1.4 seconds have elapsed? It's going to hit the floor or ground, but we're probably not there at t equals 1.4 seconds. Let's say we're here when t is equal to, we don't know it, I'm just guessing, 1.4 seconds. But that's the question, where are we? What's this distance? Okay, delta x, that's what we need to find. Delta x. And remember, there's only one formula that gives us delta x, that is v initial x times t, right? Okay, that is 30 meters per second times 1.4 seconds. 42 meters. Well, I made an assumption the assumption was that the ball would be here. That assumes that it hasn't reached the ground yet. Is that a reasonable assumption? Why don't we check delta y? Let's check delta y. Remember the formula, VIYT minus 1/2 GT squared. Well, VIY is 0 because it's thrown horizontally. Let's check this. Negative 1/2 times G, 9.8, times 1.4 squared. Negative 0.5 times 9.8 times 1.4 squared. Okay, well that's interesting because I just got negative 9.604 meters, which is actually indeed the height. So it turns out that actually you hit, I'm assuming that this 04 here is just a small error. We pretty much hit the floor with the ground at that time. Okay. So this is at 1.4 seconds. Just happened to be that way. Okay, let's do the next one, 39. A clump of soft clay is thrown horizontally from 8.5 meters above the ground with a speed of 20 meters per second. Same problem, different numbers. Where is the clay after 1.5 seconds? Assume it sticks in place when it hits the ground. They gave us a clue, I guess, but let's make sure that's the case. So H is 8.5 meters. That's the height. Well, remember, that's H, always a positive number, but delta Y will be negative H. Therefore, negative 8.5 meters if up means positive. Okay, and V naught is 20. Meters per second. Where is the clay after 1.5 seconds? Now let's do this. Let's write down the equations for the y direction. Delta y equals V naught y plus Vy final. This means final. Over 2 times t, and also we have delta y equals V naught y t minus 1/2 g t squared. Now V naught y is 0, which simplifies things, and delta y is negative 8.5. So we can solve this for t, right? So delta y is negative h. Therefore, t is equal to square root of 2h divided by g. So let's find this t, okay? This is the time when it will hit the floor. .5 16, 17, right? 17 divided by 9.8 and take the square root of that. 1.31 seconds. So it's already on the floor. It sticks to the ground. Assume it sticks in place when it hits the ground. Right? So it just sticks there at 1.31 seconds, and of course at 1.5 seconds it's still there. Alright, so that gave us the answer already. Now, could we use the first equation here? Well, no, because I don't know what the... I know what delta y is, but both Vy and T are unknown, so this equation is useless. But the second equation helped me to find T. And I didn't even bother to find where in the x direction it lands. I don't need it. Okay, but if I want it, I can find it now because I know what T is. Delta x will be V naught times T. So V naught was 20. But I didn't use 20 for, right? But now I can use it. 20 times 1.31 seconds. So this is what, 26.2 meters. All right, this was 39. Okay, let's find. I see that our range formula is in number 54. Good. Let's try, I don't know. Let's do 50. And I'm going to stop after this one, okay? A circus performer is shot out of a cannon and flies over a vertical net that is placed at a horizontal distance of 6 meters from the cannon. Okay, so what's going to happen? It's going to fly like this, of course. So the net is placed at a horizontal distance 6 meters from the cannon. Somewhere here, I don't know where, but somewhere around here. There's a net. When the cannon is aimed at an angle of 40 degrees above the horizontal, the performer is moving in the horizontal direction and just barely clears the net as he passes over it. Okay, so the net is now barely over here. He's barely clearing the net. And the velocity at that instant is horizontal, which means we've reached the maximum height. Good. That's when theta naught is 40 degrees. What is the muzzle speed of the cannon and how high is the net? So find the muzzle speed and find this height, which I'm going to call h. Alright, so where do I start? I have 6 formulas. Where do I start? The answer is simple. There is a number there given to you, 6 meters. And there's only one equation among the 6 that has delta x in it. Alright? That's the first equation, which means we have to use it. It's given, right? Delta x, which is 6 meters, is equal to V naught cosine theta naught, which is V naught x times t. All right. Now be careful. This t here is the time when the person is at the maximum height. That's the t. Not when he lands on the ground, but the t at the maximum height. Okay? Keep that in mind. Now t is unknown. Theta is known. D is known, but V naught is unknown. So one equation will not help you here. Okay? That's not going to help you. So we have to use the help of an equation in the y direction, because we know that this happens actually at the maximum height and when the velocity is perfectly horizontal. Okay, so what if we use, let's say, the delta y equation? Let's say what we have in the delta y equation. We had the two of them. The first one was something like v naught y plus vy over 2 times t is equal to delta y. But when we're talking about h here, means h, when your delta y becomes h, vy becomes 0. So you are left with v naught y, which is v naught sine theta naught, divided by 2 times t. All right? Now this equation also has two unknowns, which are v naught and t. But remember, we had another equation like that. So maybe we could use these equations together to solve for h. How? By eliminating t, right? So here we have t equals delta x over v naught cosine theta naught so this becomes v naught sine theta naught over 2, right? This came from this equation, v naught y plus v final y, which is 0, times t. So you have here delta x over v naught cosine theta naught. Now v naughts also cancel, which is good, and we're left with sine theta over cosine theta, which is a tangent. So we have here 1/2 times tangent theta naught times delta x, that is h. So 1/2 times tangent, what was the angle? 40 degrees. Times delta x, that was 6 meters. So 3 tangent 40. 3 times tangent 40. Am I in degrees? Yes, I am. 2.52 meters. Now to go to v naught from here, all right, now that we found what h is, use this one, vy squared is equal to v naught y squared minus 2g h. H is delta y, right? And vy is 0. So 0 equals V naught squared sine squared 40 degrees minus 2 times 9.8 times 2.52. Solve it for V naught. So 2 times 9.8 times 2.52 divide by sine 40, again divide by sine 40, and take the square root. 10.9 meters per seconds. All right, so I guess that's how you do it. Is there a simpler way or a different way? There is one more, I guess. You could use this. Vy is equal to V naught y minus gt. So 0 equals V naught sine 40 minus 9.8 t. You could use this. You could take that t which is V naught sine 40 over 9.8 and plug it in h. So V naught sine theta, V naught sine theta, V naught squared sine squared 40 over 2 9.8, and h is 252. But this equation is nothing but this. All right, so same thing. So you will get the same answer if you tried to use this equation. All right, so I'm going to stop here. That's projectile motion, and in the description I will add the link to the other video where I solved the range problem when delta y is not 0. Okay, so I'm going to stop the video here. Until next time, goodbye.